Next, we're going to discuss couples. First question I have for you is, what is the resultant force in this picture? So let's analyze each of the directions. Sum of the forces in the x direction equals 0. So 0 equals our two forces. We have B going in the positive x direction. We have D going in the negative direction. Since B minus D is 0, we will find that the resultant force in the x direction is 0. If we sum forces in the y direction, we'll say that 0 equals A is going in the positive y direction, C is going in the negative y direction. So once again, we're going to find that the resultant forces in the y direction are 0. The question now I have for you is this object at static equilibrium? And it should be apparent to you that although the forces, the resultant forces in the x and y directions are 0, this object is not at static equilibrium. In fact, all of the forces would be causing rotation. In this case, it would be causing a clockwise rotation. Each of those pairs of forces make a couple. And before we talk about a couple, I just want to mention a couple is just a shortcut. It's just a way of dealing with two forces that have parallel lines of action opposite sense. It's a simplification. It's not required that you use a couple. However, it will save you some time. The definition of a couple is a pair of equal and parallel forces acting with opposite sense and tending to produce rotation. The characteristics here are the two forces have to be equal in magnitude, parallel lines of action, and opposite sense. If those three things are true, then the sole effect will be rotation. Any evaluation of forces in the x direction or the y direction, you would not see anything from the couple. Now the couple is the two forces put together. The couple will produce a moment. That moment that the couple produces is constant everywhere. It can be moved anywhere in the system, and you may have experience with this if you've tried to, for example, loosen the lug nuts on a car tire while the tire is raised in the air. You will know that the tire tends to spin even though you're not trying to turn the tire around its axis. You're trying to turn the bolt on the bolt's axis, but the tire still has a tendency to spin, and that's because you're essentially producing a couple. Now, the value of the moment produced by the couple is one force's magnitude, that's only one force's magnitude, multiplied by the perpendicular distance between the lines of action. We're no longer looking at a perpendicular distance to a point. We are now taking the two forces and finding the perpendicular distance in between those two forces. In this particular problem, we have a wooden beam attached to a building over here on the left end and a series of 6 forces acting on it. The question asks that you find the resultant moment with respect to point A, which is here at the top of the beam, and respect to point B, which is down here at the bottom of the beam. As this problem has nothing to do with static equilibrium, we are going to call this a working diagram, and I just called it working diagram beam. We need a sign convention, and then we need variables on all of these forces. Now, if you look at how I've labeled these forces, I've gone ahead and labeled the forces with respect to their couple pairs. So F1 is going down 400 newtons, F2 is going up 400 newtons. They have parallel lines of action, equal magnitudes, and opposite senses. Those two forces are a couple. If we analyze the resultant force from those two in the x direction, it would be 0. If we analyze the resultant force in the y direction, it would also be 0. The same could be said for F3 and F4. F3 and F4 make a couple. Same could also be said for F5 and F6. Those two forces also make a couple. I'm going to begin by evaluating the resultant moment with respect to A. And as before, the statement should read like this. MA equals the sum of all the individual moments around point A. So MA then equals, now at this point in time, what I'm going to do is I'm going to treat each of those couple pairs as a couple. So instead of saying F1 times its perpendicular distance to point A, I'm going to say F1 times its perpendicular distance to F2. Likewise, for F3 and F4, I'm going to use F3 times its perpendicular distance to F4. You'll notice that I'm breaking F1 into its x and y components, F3 into its x and y components. You can probably see that F1 has no x component, so that's going to be 0. You don't have to write this here. I'm just writing it here to be as descriptive as I can be. And then last, we have F5 and F6, and we can break F5 into its x and y components. Now here, that actually becomes very helpful. The reason I broke F5 into its x and y components is because I don't want to find the perpendicular distance between F5 and F6. Now I can go ahead and cross out the ones of these that I know are going to be 0. So F1 has no x component, therefore F1 times d perpendicular is 0. The same is true for F3. Now coming over here, F5 x component is on this blue line. There is a perpendicular distance between that, and there's also a force there, so that's fine. F5y also has a component, it's right here. F6y has a component, it's right here, but you'll notice that F5y and F6y, although they both have components, the perpendicular distance between their lines of action is 0 because they are in the same line of action. So the y components actually produce no moment. Now we need our where statement. And we would say F1y times d perpendicular, that equals F1 times the perpendicular distance between F1 and F2, which is b. Now I've done this whole line example for you before, but if we draw a horizontal line and we look at both F1 and F2, F2 would push that line up, F1 would push it down, and you can see that those are going to produce a positive rotation. So F1 times b is going to be positive. The next couple pairs, F3 and F4. So F3y times d perpendicular equals F3 times the perpendicular distance between F3 and F4, which is a plus b. And if we want to look at F3 and F4, F4 would push the line down and F3 would push it up. So it'll cause this type of rotation. And I've defined that rotation as negative. And finally we have F5x. You remember there is a perpendicular distance, a non-zero perpendicular distance between F5x and F6x, but the perpendicular distance between F5y and F6y is 0. To find the value of F5x, that would be cosine alpha times F5. The distance between the x components is simply c. And evaluating those two particular forces, you'll see that F5's x component would push our bar that way, and F6's component would push it that way. So the moment produced by F5x and F6x is going to be negative. So now we have the moment produced by this entire system expressed in just 3 terms. You could always evaluate each individual moment and say F1 times A plus F2 times A plus B plus F3, that would be 0. Plus F4 times A plus B plus F2 times A plus B. That would work, but it would be a lot more terms in your equation. It would end up being a lot more math. So now we can plug all of those terms back into our equation. So we get MA equals F1 times B minus F3 times A plus B minus cosine alpha times F5 times C. Plugging all our values in, we find that MA equals a negative 734.641 Newton meters, which means if you'd like to write this step, 734.641 Newton meters in this direction. Since the forces, if you look at each of these moments, the moments have the force and a perpendicular distance measured between the two forces in the couple. We are not referencing any point here, we're just referencing the distance between the two forces, between F1 and F2, between F3 and F4, and between F5 and F6. Because of that, it doesn't matter what point we evaluate, this will always be the same thing. All the couples will produce moments that don't change based on the point we analyze. So in our answer box then, you'll find that MA equals MB equals 734.6 in the clockwise direction. So to sum up, couples are two forces with parallel lines of action, equal magnitude, and opposite sense. They only produce a rotation or a moment, and the value of that moment is one force times the perpendicular distance between the two forces.